Alright, hello everyone. We're into class 3 of carbohydrates now. In the first two classes, we learned some basics of carbohydrates. We learned about terms like epimers, methods like Killing-Fischer rough degradation. We learned about the entire family of capital D sugars and also went past that story how Fischer could reduce the structure of glucose finally. Now we'll want to begin with the chemistry of carbohydrates, and naturally I must have told you for our requirement in our syllabus, the three carbohydrates, the three monosaccharides will be maximum interested in are glucose, it's C2 epimer mannose, and then there is a ketohexose which is fructose. So these are the three structures, three monosaccharides, carbohydrates we'll want to begin with. We'll want to talk about their different chemical reactions, and naturally by means of their chemical reactions and the results, the structure will be further authenticated, and much more about the structure of these compounds is going to be explored. Now right away, the three structures are glucose first, CHO, this OH to the right, this OH to the left, then this OH to the right, this OH to the right, CH2OH. So this is how we draw for glucose, D plus glucose, which is the respiratory fuel, blood sugar, 6 carbon atom, aldohexose, CHO kept up, vertically up in the Fischer projection, this OH to the right, so it's capital D. This does not mean dextro or legio, I told you, this is dextro, so capital D and plus are incidentally here. It's C2 epimer, C2 epimer means the rest of the configurations will remain the same, the rest of the configurations will remain the same. The rest of the configurations will remain the same. At carbon 3, 4 and 5, at carbon 3, 4 and 5, see the configurations are remaining the same. Only at carbon 2, glucose will have its OH to the right, and at carbon 2 it will have its OH to the left. And this C2 epimer is called mannose. Mannose. Capital D plus again. And right away when we take up the structure of the ketohexose, which is fructose, which is CH2OH, C double bond O, and see it's relevant because for 3, 4 and 5, fructose will have the same configuration as glucose and mannose. It will have the same configuration as glucose and mannose. So for carbon 3, 4 and 5, see this is how we'll number it, 1, 2, 3, 4, 5, 6. So carbon 3, 4 and 5, the configurations would be same in glucose, mannose as well as in fructose. Ketohexose because there is a ketonic group, and this is where, because this OH is to the right, this is also a D sugar, but mind you, this is D minus. So this is a big proof that it could be capital D, but levorotatory. Because it's levorotatory, you call it levulose. Because it's dextrorotatory, you call it dextrose. Glucose, fructose naturally are two very common popular monosaccharides, because sucrose, cane sugar, the common cane sugar, is made up of glucose and fructose. Now going into their chemical properties, glucose, mannose, fructose, glucose, mannose, fructose, all the three, glucose, mannose, fructose, all the three with red phosphorus and HI, red phosphorus and HI, they all give N-hexane. Red phosphorus HI, causes complete reduction, 1, 2, 3, 4, 5, 6. They all give N-hexane, and if they all give N-hexane, this means they all are 6 carbon chains, with no branching of any alkyl group. So all the 6 carbon in C6H12O6 is a 6 carbon chain. All the 3 can be reduced to N-hexane, it's a normal chain. Now let's talk about a reduction process. This is complete reduction. This is how you can represent an aldose. This is how an aldose can be represented. Aldose, when reduced using lithium aluminum hydride or NaBH4, which are popular reducing agents for aldehydes, ketones, this CHO will get reduced to CH2OH, this will get reduced to CH2OH, then CHOHN, and the CH2OH. So basically aldehyde getting reduced to an alcohol. You know, the same will happen with the ketone. Ketone also gets reduced by lithium aluminum hydride or NaBH4. For aldose, it's called an alditol. For aldose, it's called an alditol. So an aldose, if reduced in this manner, will give you an alditol. It will give you an alditol. So what when you treat glucose, mannose and fructose with lithium aluminum hydride and NaBH4? You'll want to copy this at your convenience. And then allow me to clear the space. I've told you about aldose becoming alditol. And now when glucose is reduced in this manner, lithium aluminum hydride or NaBH4, it gives you glucitol. It's also called sorbitol. So glucitol, because it comes from glucose. Naturally, mannose with the same compound or similar reduction will give you mannitol. What for fructose? Glucose will give you glucitol, mannose will give you mannitol, fructose will give you, so many people tell me fructitol. There is no compound like fructitol. I'll give you a few seconds to think about it. I'll give you a few seconds to copy this and think about it. See what you figure out. Glucose giving glucitol, mannose giving mannitol. So many times people tell me fructose will give you fructitol. That is certainly not right. You'll want to think over it. Till then you'll want to copy. Glucitol will be about this becoming CH2OH. Mannitol will be about this becoming CH2OH. So glucitol will be just this compound. Mannitol will be just this compound with the rest of the structure remaining the same. So even glucitol and mannitol will be C2 epimers. Fructose is ketonic at carbon 2. Fructose is ketonic at carbon 2. I must have told you in the past, every time an sp2 carbon becomes sp3, and that carbon is chiral. Any day when the C double bond O will be reduced to an OH and an H, you can have this OH to the right as well as to the left. Because you began with a C double bond O here. When this is reduced, you'll have OH coming to the right as well as to the left. So this will get reduced to either OH to the right or to the left. Now when it's OH to the right, it's glucitol, and when it's OH to the left, it's mannitol. So fructose will give you both glucitol and mannitol. Fructose will give you both glucitol and mannitol, and this will prove that it is ketonic at carbon 2. It will prove that it's ketonic at carbon 2. It's ketonic at carbon 2 because naturally it needs to be ketonic at carbon 2 to produce both glucitol and mannitol, which differ only at carbon 2. So many times glucose, glucitol, mannose, mannitol. People tell me fructose gives me fructitol. Now fructose will have its OH to the right as well as to the left. I'll go back to the structure of fructose. I'll go back to the structure of mannose, and I'll go back to the structure of glucose. And naturally glucose giving glucitol, mannose giving mannitol, fructose giving both glucitol and mannitol will prove that it's ketonic at carbon 2. Next, let's take up a mild oxidation step. Now, when I talk about a mild oxidation step, the first reaction which comes to mind in context of aldehydes ketones is Tollens test given by all aldehydes. Then Felling's test, Benedict's test. So these are mild oxidizing agents. Glucose, mannose and fructose, when they are treated with Tollens reagent, I can call it Tollens test, or Fehling solution, or Benedict solution. You know, they're all mild oxidizing agents. They're all mild oxidizing agents. They'll only oxidize CHO to COOH. CH2OH will not be oxidized, and they get reduced. So Tollens test, and you get a precipitate of silver mirror test. You get a silver mirror test. These two are essentially blue. They contain cupric compounds, and they are reduced to cuprous oxide, which is generally red. So a red color is very visible in a blue solution. So either a red precipitate or a silver mirror test is positive Fehling's, Benedict's, or positive Tollens test. You remember, these are given only by aldehydes. Not by ketones. Glucose, mannose, fructose, all the three, glucose, mannose, fructose, all the three will give all the tests positive. Now, when they give these tests positive, this is another term used in sugar or carbohydrate. A sugar which reduces these mild oxidizing agents is called a reducing sugar. So glucose, mannose, fructose, all the three are reducing sugars. Because they reduce or are oxidized by these mild oxidizing agents. The concept of reducing and non-reducing would be a little more complicated when it comes to disaccharides. In monosaccharides, it's going to be simpler. Although the only question in your mind would be, these are tests you have read given only by aldehydes, they are not given by ketones. So with glucose, mannose, it's okay. Because they are aldoses. You will wonder why fructose, how a ketone can give a positive Tollens or a positive Fehling's. Fructose gives a positive Tollens, Benedict's, Fehling's test. Fructose also behaves like a reducing sugar. It reduces mild oxidizing agents. You do not expect ketone to give this, but certainly in aldehydes, ketones, you were taught when it's an alpha hydroxyketone, alpha hydroxyketone can give a positive Tollens test. So all the three behave reducing. You will want to again copy this at your convenience, and I'll tell you something very interesting. An interesting fact is Tollens, Benedict's, Fehling's, they're all alkaline medium. Tollens is alkaline silver nitrate. Again, Fehling's, Benedict's, having citrate, tartarate ions are ammoniacal solutions. So they're all alkaline solutions. In alkaline medium, glucose, mannose, and fructose. In alkaline medium, glucose, mannose, and fructose. Glucose, mannose, and fructose. Alkaline medium will rob them of their alpha hydrogen, and something like enolization will happen. Now, when you convert a ketone to an enol, ketoform to an enol form, which is for an aldehyde again with alpha hydrogen. See if this is the alpha hydrogen used in tautomerism. For glucose mannose, this is the alpha hydrogen, and if this alpha hydrogen is gone, and used in enol formation for glucose and mannose, see this is an enol I can draw. CHO will become CH2OH. Now naturally this will be double bond COH. Now it doesn't matter. You put this OH to the left or to the right. You can put this OH to the left or to the right, doesn't matter. The rest of the configurations will remain same. Because they are same for glucose and mannose. See, alpha hydrogen or the position of the configuration at carbon 2 differentiates glucose and mannose. With this hydrogen gone and this being the enol, first of all, it doesn't matter this OH is to the right or to the left, because this is not chiral. This carbon is no longer chiral. This is not chiral. So this Fischer projection and this OH right or left does not matter because it's not chiral. The rest of the configurations are identical for both. The two were difference only at carbon 2. The difference was only at carbon 2. The chirality at carbon 2 differentiates glucose and mannose. And if this chirality is gone in the enol, can I say this is a common enol for both of them? This is a common enol for both of them. This is a common enol for both of them. Talking about fructose, this will become OH, and this can use this hydrogen as well as this hydrogen. It can use this hydrogen as well as this hydrogen, because this is an alpha hydrogen, this is also an alpha hydrogen. So here two enols are possible. But in case it uses this hydrogen, this hydrogen, then C will become OH, this will become OH, this hydrogen will be gone, this will be certainly CHOH. I'm sorry about that. With this hydrogen gone, this will become OH. This is the enol for fructose. This is the enol for glucose and mannose. This is the enol for fructose. And fructose can give you two enol because there are two alpha hydrogens possible. But if this alpha hydrogen is gone, fructose can also give you this enol. It can also give you this enol. So if you understand properly, glucose, mannose and fructose, all the three will have this common enol. This is the common enol. This is the common enol for all the three. In alkaline medium, they'll give you a common enol. So essentially what happens in alkaline medium is, whether it's glucose or mannose or fructose, and you'll want to follow my language very particularly. In alkaline medium, whether it's glucose or mannose or fructose, in alkaline medium, in alkaline medium, because of the common enol, you know what do you mean by the common enol? This means this can form this, go back, this can form this, go back, this can form this and go back. All the three will have a common enol. Whether it's glucose or mannose or fructose, by the common enol, glucose can become mannose, which can become fructose, which can become fructose, can become mannose, mannose can become glucose. So glucose or mannose or fructose in alkaline medium will be glucose and mannose and fructose. Which means where the common enol, glucose, mannose, fructose will coexist in alkaline medium. So in alkaline medium, alpha hydrogen gone, the two will have the same enol. One kind of enol of fructose will be the same as the enol of glucose and mannose. So glucose or mannose or fructose in alkaline medium will become glucose and mannose and fructose. And this is exactly what happens. Molecules of fructose in alkaline medium get converted to glucose and mannose. Some molecules will get converted to glucose and mannose. And because some molecules get converted to glucose and mannose, which have free CHO, those molecules which get converted to glucose and mannose give a positive test. So this is how fructose, despite being a ketone, behaves as a reducing sugar, reduces tolerance, Fellings, Benedict's, because in alkaline medium, fructose gets converted to glucose and mannose. And this arrangement or rearrangement is called Lubri-de-Bruyn. It's called Lubri-de-Bruyn. Pretty big name. Alberta Van Eckenstein rearrangement. So it's a long name. So many times it's called Van Eckenstein rearrangement. So many times it's called Van Eckenstein rearrangement, or it's called de Bruyn-Eckenstein rearrangement. So in the real exam, you might have a shortened name, but this is the complete name. Lubri-de-Bruyn Alberta Van Eckenstein rearrangement is about glucose or mannose or fructose in alkaline medium existing as glucose and mannose and fructose. And only because fructose molecules could get converted to glucose and mannose, fructose also starts behaving as a reducing sugar. All of this has to be understood because this will happen only in alkaline medium, and Tollens, Fellings, Benedict's, they are all alkaline, and the same will not happen in a acidic medium. This is mild oxidizing test, Tollens, Benedict's, Fellings, which is in alkaline medium. Suppose if we use a mild oxidizing agent, which is going to be an acidic medium. Very popular is bromine water. Bromine water is very popular for two reasons. One, bromine water test is at a pH less than 7. So that's under acidic conditions. And two, bromine water being colored, a color change will be a good test to perform. A color change is a good test to perform. So this is what is happening because of Lubri, De Bruyn, Alberta, Van Eckenstein rearrangement. All the three will behave reducing. They can get interconverted via the common enol. And we'll want to talk about the next reaction, which is again a mild oxidizing agent, this time involving bromine water. Glucose and mannose with bromine water. Glucose and mannose with bromine water will get oxidized to gluconic acid or manic acid. This is what happens. If this is an aldose with bromine water, only this part gets oxidized. So this becomes COOH. This N is about the length of the carbon chain, whether it's an hexose or a pentose or a tetrose. So if this is an aldose with bromine water, it gets oxidized to an aldonic acid. So glucose will become gluconic acid, this will become COOH, this won't get oxidized. Mannose will become manic acid, this will get oxidized, this does not get oxidized. Gluconic acid, manic acids will also be C2 epimers. Fructose with bromine water, no change in color. Naturally, with bromine oxidizing with this reaction maturing, bromine water will lose its color. Fructose, no color change. And this is how you can differentiate glucose, mannose and fructose. It's a popular difference. Glucose, mannose will give a positive bromine water test. Bromine water will get decolorized. Fructose will give a negative test. Bromine water will not get decolorized. Let's talk about a stronger oxidizing agent. I did tell you about it in the last class while we were converting aldose to alderic acid. When we were converting aldose to alderic was when both ends become COOH. Alderic when both ends become COOH. So this is alderic. And it will require a stronger oxidizing agent. The most popular being nitric acid. Nitric acid is a strong oxidizing agent, which converts aldose to alderic acid. So the next set of reactions will be using nitric acid. And now glucose with nitric acid. Naturally, both ends becoming COOH will give you glucaric acid. Now glucaric acid is also called saccharic acid. Mannose with both ends getting oxidized, will give you mannaric acid. Yet again, glucaric and mannaric acids will be C2 epimers. This is how it can be generally represented, aldose getting oxidized to alderic acid. And now fructose with nitric acid. Nitric acid is a very strong oxidizing agent. It can break ketones. Aldehydes are easier to oxidize because it's a terminal group, can become COH readily. Nitric acid is a very strong oxidizing agent. It can break ketone. And you remember, there was a particular rule called Popoff's rule. Where if a carbonyl or a ketonic group is broken, it goes with the smaller alkyl group. So suppose if it's broken in this way, so that this goes with the smaller alkyl group, I'll mention the name. It's called Popoff's rule. Expect two fragments. This fragment would be oxalic acid. This fragment would be oxalic acid, and this fragment, this will become a COOH, 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 and naturally 4 and 5 having identical configuration, this tartaric acid will be mesotartaric acid. This will be mesotartaric acid. You know about tartaric acid, you know about this will be mesotartaric acid having a plane of symmetry. That will also prove that carbon 4 and 5 have identical configuration. Naturally, this gets oxidized to COOH. Two fragments, oxalic acid and tartaric acid. So this is how the three popular carbohydrates react with nitric acid. There are more reactions by which it can be proved that glucose, mannose and fructose have related structures, that at carbon 3, 4 and 5, they have identical structures. One such very popular reaction is reaction with phenylhydrazine. So you'll again copy this at your convenience, and we'll take up that particular reaction, which is reaction with phenylhydrazine. Hydrazine gives you hydrazone. Hydrazine gives you hydrazone. This is glucose and this is mannose and this is fructose. So hydrazine gives you hydrazone. And in sugars, there's going to be very peculiar, because generally this is what you do. CHO, you remove water. But this is a very peculiar thing which happens with sugar. in sugar. First of all, these aldohexoses, suppose I'm drawing glucose for the time being. They react with 3 moles of phenylhydrazine. Naturally, it can be drawn in this way as well. They react with 3 moles of phenylhydrazine. We are used to removing water in this manner. This is what you do in aldehydes, ketones. And generally, a hydrazone will have C double bond N NH a ring. But here they'll react with 3 moles of phenylhydrazine, and aldohexose reacting with 3 moles of phenylhydrazine will give you something like this. This is expected. Now you have something very similar here. 2 moles get incorporated. And then the rest of the structure, carbon 3 will have OH to the left. Carbon 4, carbon 5 are not affected. So this will also prove, before I go there, 3 moles where 2 moles get incorporated like this. The byproducts are aniline and ammonia. So this takes care of the third mole. We don't want to go into the mechanism because that is not relevant, but this is what happens. For aldohexoses, both these carbon atoms are affected. Now the phenylhydrazone of a sugar has a very particular name. They are called osazones. And osazone formation, because they are crystalline solids having specific melting points, osazone formation is a very popular way for detect a carbohydrate. Because a carbohydrate will give you a particular osazone with a particular melting point. So from the melting point of the osazone, maybe you can predict the structure of the carbohydrate, but you cannot predict the structure at carbon 2, because once you have the osazone, both the chirality of these 2 carbon atoms are gone. This was not chiral to begin with, but at carbon 2 the chirality is gone. So osazone formation is good at detecting carbohydrates, but it can never differentiate between C2 epimers. Because see, with the formation of osazone, chirality around carbon 2 is gone. 3, 4, 5 is the same in glucose, mannose and fructose. You will want to again copy this at your convenience. Generally, osazones, being crystalline solids, are used to detect carbohydrates, but they will fail for C2 epimers, and certainly an aldose with a ketose where 3 to 5 is identical. So, just in case it's glucose, and I tell you even mannose and fructose, if I tell you even mannose and fructose, this is glucose. If I tell you that I began with glucose, but even mannose and even fructose with phenylhydrazine, 3 moles of phenylhydrazine, if all the three give you the same osadone, glucose, mannose, fructose, they give you the same osadone, this will prove that around carbon 3, carbon 4 and carbon 5, the chirality or configuration is same from C3 to C5. This will prove that the configuration is same from C3 to C5 for glucose, mannose and fructose, all the three, because all the three give you the same osadone with the same melting point. So these are some facts which will help you in relating to these structures. We have certainly proved in different manner that this is ketonic at carbon 2 and 3, 4, 5 is identical in all the three. Certainly glucose, mannose are C2 epimers to begin with. And then finally we take up the reactions which are not given by glucose. So far we are talking about reactions which are given by glucose. Now let's talk about the reactions which are not given by glucose. Reactions not given by glucose. Now reactions not given by glucose are the following. Very popular reactions. As an aldehyde, it's supposed to react with sodium bisulfite. Sodium bisulfite addition is a very popular addition. Ammonia, Grignard reagent, it doesn't react with Grignard reagent. Gr, it doesn't react with Grignard reagent, which is a very reactive compound. We speak about how aldehydes with Grignard reagent, ketones with Grignard reagent can give you a variety of alcohols used for synthetic reasons. Sodium bisulfite addition, condensation with ammonia, Grignard reagent, glucose doesn't do any of these reactions. There is no reaction with Schiff's reagent. There is no Schiff's test. This is a basic test for an aldehyde. No Schiff's test. It doesn't give the popular Schiff test for an aldehyde. And there is this third phenomena which is very important and unique to the chemistry of carbohydrates, mutarotation. We'll talk about it in details. In all likelihood in the next video, glucose is going to exhibit mutarotation. Now, as I did tell you, this fact, mutarotation, will be completely new and unique to the concept of carbohydrates. Mutarotation is going to be a new phenomena altogether, very unique to the chemistry of carbohydrates. We'll talk about mutarotation in great details in the next video. But certainly, so many popular reactions given by aldehydes, not given by glucose, would prove that our understanding of glucose via the Fischer projection so far is not complete. Because with the presence of a free CHO, glucose or rather mannose even, and so many aldohexoses would have given these reactions. These common aldohexoses will not give these popular tests given by an aldehyde. So certainly our understanding about the structure of glucose is not perfect. Rather, in the next video, it's going to open up new chapters altogether. We'll see the principal form of glucose will be a ring form. So far we have been taking up the open chain form of glucose in the Fischer projection. Now we would want to know that the principal form of glucose will be a ring form. We'll want to know about another term called anomer. Like we got started with epimers in class 1. We'll understand about anomers when we take up the ring structure of glucose. Don't worry, I'm going to take you past all of that in great details. Anomers, mutarotation, and all of that would be very interesting. We'll take up all of that in the next video. This much for the time being. Thank you so much.